So if you get your diagram drawn using Logic Pro, and everybody should have that out of their book, right? Does it come in the textbook now, or does it come in the lab book? Text. That might be. That's right. So on mine, I have Shift, and then right here I have a print screen right here. So I hit Shift, print screen, and then you can come up here and then bring up Paint. Now, if you don't have Paint in your Start menu, you can just go to All Programs, and it's usually inside Accessories. You can go to Accessories, and then Paint's usually in here. And then when you bring up Paint, right here it says what? Paste. So this is the screenshot I just took. And what you can do here now is you can save it. I can't get to it. And then attach that file to email, right? Everybody okay on how to attach that to email? Yes or no?
No, that's okay.
Well, if you use, when you send it to me, what are you supposed to use? So if I had a Logic Pro diagram up, so this is actually what I took a picture of, by the way. So I'm not going to save this. So if I had Logic Pro up, I don't know what diagram is up here. And this is the one I was going to show y'all anywhere today. I don't know why I didn't think about it when we was talking about examine on, examine off. I didn't know why I didn't bring up this and show y'all this so y'all could understand it. Okay, so this is my ladder diagram. Now if you put your DVD in there when you run it, if you don't put your DVD in there when you run it, I guarantee it's going to pop up and say you got a 15-day trial version. But if you put your DVD in there while you're running the program, it should come up there and allow you to print it. And then you can bring it in that way. That would be fine. Attach it to it. But if I'm going to do this, okay, so I got it up here, and I can hit what on mine? Shift print screen. Okay, then what I'm going to do now is I'm going to minimize this. And then I'm going to go up. I'm going to bring in what? Paint. And then I'm going to hit what? Paste. And there it is right there. Okay. Now what you can do, see this right here, what you can do where it says what? Select. So I'm going to click on that. And then we can literally come in here and just clip off all this other stuff. And then I can do what here? Crop. See what I just did? And then what can I do? Yeah, then I can put save as. This is a new picture, and any one of these formats are good. I usually use PNG, which is a Windows format for saving this. Of course, normally what happens if you don't have extensions turned on your computer. So basically, a file consists of two different things. It consists of what we call the name, which is this on the left-hand side. And then it has what we call an extension. What separates the file from the extension is a dot. Now, what that extension does, it tells the operating system what program that file belongs to. Because when you double-click on a GIF file, well, a GIF is not a program, a GIF is a picture. But it's got to load in a program that allows you to do what? Display that picture. So we set up what we call file associations. I don't know if you ever seen it pop up there where you double click on a file and a box pops up and says, what program do you want to launch this thing with? Well, the problem is there has not been a file association set up. You can change those too. You go to folder options and you can look at view and it shows you all your file associations. Most people turn, by default, Windows comes in and does not display extensions on what they call non-file types. So if you got an association set up between a data file and a program file, then Windows won't display the extensions. You can do that in folder options too. Let's see where folder options are. On Windows 7, I think it's in Control Panel. And then the folder options. and then here's view. So this is what you would do. So what you want to do is you take off this hide extension for known file types. And then that way you can see your extension. So every application has extension, not applications. Every file has an extension. So once you turn your extensions on, if you see any EXE or COM extensions, those are programs. And that's what gets people screwed up when they bring an email. They'll put a link down there and they'll put a .com. Well, guess what? .com is a program. And you click on that thinking you're going to go to a website somewhere, which what you're doing is running a program that's attached to that file. And then once you run a program, then that program, if you don't have a real good virus checker, that program can set up just about anything you want to. The internet, especially up the East Coast, they wiped out the internet, this weekend, because they did what they call a denial of service. And what they'll do is they'll come in and they'll install a program on your computer so they can use your computer like I said. And they'll tell your computer to generate all this email or all these access to the website, and they have thousands and thousands of these computers that people have this little Trojan horse stored on there. And then they generate so much traffic to that one website that people that once you use it can't run. And yeah, they just pop it. So you need a really good virus checker installed on your computer. Here we use Kaspersky. If you're on Bright House Network, they give you a virus checker as part of your account, McAfee's, which is a really good virus checker. So if you're on Bright House Network and you don't have a virus checker on your computer, or you're going out and buying one and paying $50, $60 a year, you're just wasting money. Go to My Bright House. I don't know about Charter. Of course, I know Charter and Bright House are the same now. Charter bought Bright House. Huh? Yeah. So most of your ISPs, your internet service providers, give you a virus check. Well, I don't see. I'd have to see where you get to file associations now. There's a way I'd have to look at it, but anyway. And I'm not going to say this. What we're going to do is we're going to look to understand PLCs. We need to do a little work with inputs and outputs, a lot better than what the book does. So this is eventually going to be split up into two presentations. Right now I stuck it on one on basic math. So we'll talk about inputs and outputs. Because what came up, of course, the other class was what we call examine on and examine off. Now, if you're running MicroLogic, you can change it just by, so this guy's set up for what? Examine open, excuse me. This guy right here is set up for examine close. Now, the problem we have is that when I look at the IOs on the PLC, and by the way, on Allen Bradley, so you got this guy right here. It's called inputs, and you double click on this, and it actually shows you what's going on those inputs. Okay. And of course, this won't do anything unless it's running. What I'm going to do is I'm going to come up here and download this and run it. Okay, and then I'll bring up the tables again. Oops. And we'll look at the inputs. So over here I have a normally open, and I'm using inputs 0 and 1. So the first port you have, the first inputs available on this is 1. Now this is the big difference between Siemens. Allen Bradley runs in groups of 16 of words. Then Siemens runs in groups of 8 of bytes. So that means if I had a 32-bit input module, it would actually take up 2 module numbers, right? Does that make sense? So here, this is, they're using groups of 8, so we've only got 16-bit input, 16. I notice I'm using 0 and 1, and right now they're both 1. Okay. Now we have, so this is the actual, what's actually going on the input. So when I come up here and I press this button right here, oops, let me put it in run, sorry. I come here and press this button right here, what do I get over there? I get a 1. And when over here, it's released, it gets a 0, right? When I come here and press this, I get a 1, I get a 0. Okay. Y'all understand that? So it don't make any difference if you're using the examine on or examine off. If you have your port set up, when the device it's looking at is made, you get a what? 1. When it's not made, you get a 0. Okay, so that don't change whether you use the examine on or examine off. But when we bring that 1 and that 0 into a program, is a 1 true or is a 1 false? A 1 is whatever you make it. In fact, the RS-232 interface uses a negative voltage for a 1 and a negative voltage for a 1 and a positive voltage for a 0. So what we're saying is up to the program to decide what is a true and what is a false. Y'all understand that? So a 1 is not all we're dealing with digital is we got a 2 states. Right? You understand? Y'all understand? Not high and low. A high and low is always a high and a low. A true and a false is whatever you want it to be. Y'all understand that? A high is always a voltage and a low is always a 0. So we don't say high or low. When I say true or false, which is what your PLCs are looking for, your PLCs are your program is looking for a true or a false. And what's the truth? Whatever the program looks for. And that's what you're doing when you do examine on and examine off. You're changing the meaning of a true and a false. Y'all understand that? So right now, I have this guy here set up for, this guy right here is set up as a normally closed. And I have it set, I can't see it, I'm going to have to go offline. Okay. I have this guy set up for examine close.
Or you got it set up for examine open. It says change to close.
I'm sorry, so I've got this one set up for examine open.
Okay.
The top one's set up for examine close. Now if you don't change it, by default it comes up to be examine close. So you have to go and change it to what? Examine open. Examine open. So if I was to write this down, then this is the way it works. I had to make a note so I can make sure I do this right. Because we got a little problem there with class. So this is what I'm going to bring up Microsoft PowerPoint so I can do some writing. So we got 2 states, right? You understand. So let's look at examine close. Then what we have here, if the input is open, we get a 0 out of it. Oh, I'm sorry. I left off something. We get a 0 from the switch. If the input is closed, we get a 1. Now over here on examine open, if the input is open what do we get? We get a 0. If the input is closed, we get a 1. So the switch don't change, right? You understand? So if it sees a closed input, it gets a 1. If it gets an open input, it sees a 0. Now what we have here is up here, this is false, this is true. That's what the PLC examines that at, right? You understand? Down here, this is going to swap. If this is true, this is going to be false. You understand that down here? So down here, if it gets a 0, the PLC interprets it as a what? True. If it gets a 1, the PLC interprets this as a what? False. Up here, if the PLC sees a 0, it's going to interpret this as a what? False. If it gets a 1, it's going to interpret this as a true. Y'all understand? So when you say highs and lows and ons and offs, that's not what the PLC is looking for. It's not looking for highs. It's not looking for lows. What it's looking for is, that's not exactly true. It is looking for highs and lows, but what is a true and what is a false?
It doesn't matter what you place the switch is in the program.
Yes, it matters a lot. Because one thing is that stop buttons, especially E-stop buttons, according to OSHA, they have to be normally closed. Because if you got a normally open switches and one of your contacts wears out, which they happen all the time, they won't walk. They won't work. And you're sitting there beating on that normally open and it's got a bad contact and you're beating on it, right? You understand? And things don't stop.
I mean, I understand the physical switch needs to be whatever. I'm saying if you can change a normally closed contact to examine it open.
Well, let's look at it. Let's run the program. So here we have 2 of them. Okay. And this is a normally closed, so it's showing it as yellow. Let me go ahead and switch it to run. I don't need to download it again because it's the same program. Okay, so this guy right here is the normally closed. Right, the top up there is normally open. Okay, so what do we have? Now notice this guy right here is got a 1, and it's running. Okay. You'll see this? So this guy is set up for what? Examine close. This guy up here is set up for what? Examine. No, this is set up for examine closed. This right up here is set up for, this guy is set up for examine open. Okay. But look what I'm using over here. So this is examine open. So what it says right now, it's open, so it's true. So it's open over there, so it's true. So it indicates the contact is closed because it's what? It's true. And this guy right here is entered that. But look what I had to use over there. Look at 1. What did I have to use? I used a normally open switch. Because it's examine what? Oh, if open. Well, if it's examined, if it's open, it's what? It's true. I'm sorry. It's true, right? You understand? I'm sorry. Examine if open, but I drew it as a what? I chose it as a closed switch. Okay? But it's true over here if it's what? It's open. So if it's true, if it's open, then I drew it as a normal closed switch. Right? You understand that? Yes or no?
So on the ladder, it will be reverse of on PLC.
Yes. If you use a normally open switch, well, what's the problem? So what I'm going to do is I'm going to change this to a normally closed switch. This is set if examined if closed. So now it's true. It's closed, right? You understand? Over here it's true if it's open. But I don't, but so it's true if it's open, right? You understand? Yes or no? One.
Be false.
Yeah, so down here we have, I'm sorry, so that over here we got what?
Zero is close. Zero. So that's gonna be a false.
So let's look at our, inputs and outputs. So right now, one is what? No, well,
It's a high.
so input one is input zero is a one. Input two is, input three is a,
You gotta go to
Oh,
the
sorry.
left.
We use 0 and 1.
what's one then?
You're at the same zero.
Oh, I'm sorry. Yeah, sorry. So this right here is, this is, okay. This is
True.
true.
Right, straight, false.
Well, that's what the tendency people have to do, is they want to say a zero is false. But that's not true. That's not true. That's false. Examine close. If I got a zero, it's what? False. If I got a one, it's true. So on examine open, if I have a zero, it's what? True. Okay, y'all understand?
So both of those are true.
Yeah. And that's the problem you have, because for some reason, when you talk about truths and false, people associate truths and false with ones and zeros. But a true and a false in a digital world can be whatever the programmer looks for, or what the programmer looks for. So what they've done, and it makes it nice, because if I'm using a normally closed push button, it's a lot better for me as a manufacturer to buy all the same push buttons. So if I bought all normally open push buttons, there's no way in the world my technician could put in the wrong push button, because that's all I got. Right? You understand? So this is where we would use what? We would use examine open. If I wanted to use a normally open push button to represent a normally closed contact. That way a one will always be true and a zero would always be false. But the problem is OSHA says that stop buttons, especially e-stop buttons, have to be normally closed. Because that way if one of your contacts goes bad, you can't start it. Because you always see a lock. You always see it open. But if it's normally open and one of your contacts go bad, then you're not going to be able to stop. So I don't know about stop buttons, but I know for a fact an e-stop button has got to be a normally closed contact. Which gets us a little confused, because in motor controls we use a normally closed contact as a normally closed symbol. Right? You understand? In PLC, we use a normally open contact symbol for a normally closed push button. Y'all understand that? So if I use normally open push buttons, then I have no problem. I just call them, I just say, I use a normally closed symbol, right? You understand? Because when I press it, it becomes, because when it's released, it's what? False, and when I press it, it's true, right? So it's going to change settings. So guys, I don't know how else to show y'all that. So especially on e-stop circuit, you don't have to use a normally closed contact, but I want it to be true, right? You understand? So what's that? If it's pressed, it's true. I'm sorry, if I get a 1 back, it's true. Right? You understand? The problem is, if I get a 1 back, I gotta use a what? Normally open contact, or symbol, not a normally open contact symbol. So this is examine on, examine off. But what it ends up with, it ends up our symbols being,
TLC, we use a normally open symbol for a normally open.
well, if we use examine on, I'm sorry, if we use examine close, we use a normally open symbol for all our inputs. Now, we're not talking about relay contacts. Relay contacts is not the problem because we don't hook up relay contacts to an input, right? You understand? So if I'm using normally open contacts, if I'm using all normally open push buttons, then I've got to use examine close for every input system. Huh? And then you use a normally closed switch, right? You understand? Because that means it's true and it's going to do whatever it's supposed to do. So if you get into a PLC diagram and all the inputs are drawn as normally open, you know, whoever programmed that used what examine close. But if you get in there where you got if you see this on an input, not on a relay contact, don't get outputs confused with inputs. So outputs are either turned on or turned off, right? You understand?
So what
Inputs, you have to determine what is a true and what is false.
what would be the circumstances where you would change examine open?
Well, a lot of electricians have a problem with using a normally closed input, a normally open input for a normally closed push button. And they think that they got to do what? Now, plus we have, and this is what we're fixing, these sensors. When we hook up sensors, some sensors use what we call a positive as a common. Some sensors use a negative as a common. And we call them NPN or PNP sensors. We're going to look at that a little bit. Well, PNP sensors, you got to set them up as examine open. NPN, you would set them up for examine close. And that's one of the big differences on, it's not push buttons, it's what? It's sensors. When you get into sensors and you figure out which ones you got.
So on PLC, for each button, it's examine close.
What are you looking for? This? This?
E-stop.
For anything. Yeah, we use, normally what we do on, if I'm using switches, we should use examine close for everything. When we start using sensors, that's where you have to figure out which one you need to use. Because sensors connect to input ports, right? You understand that? All you do down here is you have a little switch that you flip that represents a temperature sensor. You have a switch that you flip that represents a watt. All these different sensors that we have out there. This book has a pretty good section on sensors. And we do teach a sensor class.
So normally open is going to default to examine close, and normally close is going to default to examine open.
On which mean default? No, there's no defaults. The default is examine close. So no matter what you put in there, it defaults to what? Examine close. So how many of you ever went in there and changed that? Yeah, because it defaults to what? Examine close. Y'all know what the default in computers is. When you got an instruction that requires information, and it requires it, then what the operating system does, probably 90% of the time, is stick something in there by default. Default means what it uses if you don't want, if you don't change it. That's what a default is. So every PLC that I've ever dealt with, it defaults to examine close. And you have to change it to what? Examine open.
E-stop is already automatically examine close.
Every input instruction you put in a PLC is defaulted to examine closed. So you can't say an e-stop button. An e-stop button is nothing but a normally closed push button that latches. So an e-stop button latches when you hit it. And you deliberately got to do what? Or most of them, you have to twist it and pull it out. So that means when you hit it, you break it, and then you twist it and have to pull it back out. So e-stop buttons cannot be normally, it cannot be momentary contact push buttons. They literally supposed to lock. And now ours don't do that, but ours has a switch on. These disconnects right here have a switch on. So these e-stops don't latch down, but to get it back, what you gotta get a dang key in. You can pull it out, but you gotta get a key and put it out. Now, I don't know if these come out now, if that e-stop's like that or not. So you gotta, on our motor controls, you don't have to turn it and pull out the e-stop, but you gotta have a key to enable it. And unfortunately, some people leave those keys in the slot. So you can't say a normally closed defaults to examine closed. They all default to examine closed, right? So right off the bat, this guy right here is true because it's getting a what back? 1. So it shows it yellow, which means what on Allen Bradley? It means current is getting through that contact. Okay, y'all understand? But wait, it's a normally closed contact, and up here it's normally drawn as what? Normally open. And that's what gets people confused. That's what gets electricians confused, is how can you have a normally closed contact over here and draw it as a normally open contact in your PLC program? Right? Because when it's closed, it's what? So what people get confused with is they get confused with a normally closed, a mechanical normally closed relative to what the PLC sees as a what? Sees as a true or false. Or y'all understand that? But over here, that's a normally closed contact, but when I look at 1 over there, it's normally open. Because now a 0 is a true. Right? You understand? So it's true. Is it closed? Is the contact closed over here? Does it appear to be closed? Yeah. On input 1.
But it's examinable.
It's examined, but it's saying it's true is if it's what? If it's what? Yeah, it's examined and open. Is it? So is it what?
It's still true.
It's true. Well, by George, it's true. So that's why, and it's a normally closed contact, and it's true.
Okay, so the examine open and examine close is referring to the switch. It's not even, we don't care about the contact. Is that what I'm hearing, what I'm understanding?
It's determining what it's getting back from the input.
From the switch.
Well, from the input. You keep saying switch, but what can we hook up to these inputs? We can hook up anything that gives us a signal, right? So we're looking at nothing but push button, but in the automated, we went over there to the line. What did you see hooked up to the inputs of those PLCs? All kinds of stuff. All limit switches, photo sensors, metal detectors, capacitive sensors, ultrasonic sensors, they were all hooked up to them. Okay, y'all understand that? So when it sees a closed contact, not a switch, when it sees a closed contact, if it's examine closed, so this is what? Okay, this is true. That's true.
Right. It's an open contact. And that
But it's what we,
I'm drawing right there.
yeah, but we got it. Yeah, don't get this confused right here, right? You understand? Okay. okay? So it's drawn as a close contact. So a close contact means, okay, if what it's looking for is true, then it's closed. Examine closed says, well, what if I'm looking for is open, it's false.
That's the problem. I was trying to relate it directly to the contact.
To the symbol.
Right.
Instead of what's true and what's false. Okay, y'all understand. So here I'm getting a what back? True. Here I'm getting a true. Right, you understand. Well, it's a normally closed contact. So is that true or false? Well, that's true, right? You understand. So that's why it's showing closed.
So if you have all you have available, you've got to change that normally closed contact to it. And all you've got available is normally open.
Well, you do that.
You can go on PLC.
Yeah, or you got a PNP sensor, and the only thing you can get now is an empty instance. Well, see, now you gotta go in and change what's true and what's false, right? So normally it doesn't come into play on push buttons. Push buttons means, okay, what we want to do is we're gonna use, probably examine close. When you get to these sensors is where you're gonna have to make a decision on what the sensor gives you back when it's what? When it's true and when it's false.
Whether it gives you power or don't give you power.
Right, whether it gives you a ground or 0, or whether it gives you power or 1, right? You understand? So I might have a certain sensor that if it gets above a certain temperature, it gives me back a 0. Right, you understand? Well, we'd have to change that over to what? Examine open. So that's the only time that I know of that it comes into play, and that you will probably have to do what? And so if I came up here and redraw this as a normally closed contact, let's do that. I'm gonna put it back to program. And I'm gonna come up here and I'm gonna change this to this, right? And then I'm gonna download it and run it. And now it's false.
Because you got this picked up on.
Yeah, so this is, right? This is true. So y'all understand what we're saying?
Normal closed.
Use normal closed input with the examine closed. So it's true all the time, right? Because it's all it. So that's, it's false all the time. So this is the examine open, and I got a what? I got a normally closed push button. I got it set for examine what? Open. So what's it do? What's it give? It's false. And so the normally closed contact is false, right? You understand?
So that would give you an error with it.
What do you mean by an error? It wouldn't work. I mean, you don't get an error unless you screw something up, right? If you don't build that rung correctly. So this is not an error. The PLC has no idea what you're trying to do. It does, okay, it knows you can't put coils in series. It knows you can't put this there. It knows you can't do this. If the rung has got the correct syntax, then you're not going to get a what? Error. But if you use a normally closed contact symbol, it has no, and you use the right symbol, that's not, your PLC is not going to give you an error, right? I mean, we say in programming, you know, when you compile a program or compile it over to your PLC binary language, all it knows is if the syntax, and the syntax, what is syntax, by the way? S-Y-N. It's the way things are written. Of course, in PLC language, it's drawn. And that's all it can check for, is if it's drawn correctly. Not if you meant to use a timer, you put a timer in there and you wanted to use a counter, is it going to give you an error? No. Because you used the right symbol, right? You understand. If you use the right, but if you try to put two contacts in series, or you leave an open rung, or you forget to put an output out there, or something like that, then you're going to get that big red E that pops up over there, because now you got a what? You got a syntax error. Yeah, these are no syntax errors, right? But I screwed up on the top one because I'm an electrician. I think, by George, I gotta have a normally closed contact for a what? For a stop button. So we're using our normally closed contact out there. You gotta use the normally closed symbol. You do in motor controls, but not in PLCs, because PLCs, what you're changing is what it sees as a true and what it sees as false. Come on, gotta hurry.
Oh, Rich, in, starting with, input 0, the reason that's false because it doesn't match. It won't light it up, right?
I don't know what you're
Okay,
asking.
all the way over here where it says IO simulator?
Yeah, so what we got here is we got this set up for what? Examine open.
But the reason that whole line is false because these two don't match to make the highlight false, to make the output false.
Because the switch is off.
Right, and in input 1, the reason that's true because
It's
the output is on.
But right now, both of them are examined open.
Yeah. So the top one's examined open and the bottom is examined open.
Right.
But
Okay.
only one of them is true.
So over here, only one of them's true.
Input 1.
Input one.
Or run 1.
Yeah.
All right.
Because it's examined open. Well, is that open? Is that open? Is one open? Okay, so that means if it's examined open, that's true.
Right.
Okay, so that means this normally closed contact would be true. Okay, understand? Right? Because I'm getting a 0 back. So I get a 0 back, that makes it true. Now the top one, we got that set up for examine open,
But you got the switch.
but you got a normally closed switch. So that is what? False. So that means this one's not picked. Since that's false, that's not picked up, right?
Could you show Alfred the little click on it for how you tell that examining open and examining closed?
Oh, you mean the actual activity?
No,
Slide
just
right,
right,
sir.
right,
Slide
right,
right.
on the symbol.
Huh?
On the symbol.
Right click on the symbol.
Now you know that's examining open.
Yeah, because we,
Just change examining
Second
closed.
from the bottom.
right here.
You know they don't.
So that's why we use normally open input symbols for normally closed contact. And guys, that's as simple as I can make it. So I know it's confusing, but. And that's what people have in their mind. They think a false and a true has to be a what? A 1 and a 0. But no.
But then that changes.
So what we're going to look here, we're going to look at syncing, sourcing, input, syncing, sourcing, output. We'll do a real good job talking about.
What sugar is
This is a little bit in. You can look in the index and look up syncing or sourcing. Any one of those, and it should take you there. Very, very small write-up. But this becomes very important on how we hook up outputs and how we hook up inputs. Push buttons, this right here really makes no difference. So when we get to sensors, it really starts making, it's whichever. What page is it on, guys? This is one of the first chapters.
It's on Thursday.
So this is some terms. So field device, any device that connects to a PLC input or output. So when you look through Alan Bradley handouts, when you start looking, doing internet, they're going to start talking about field devices. And these are devices that you connect to the PLC that's not part of it, right? I understand that. I've seen some power supplies be called as a field device. Syncing, a method of connecting DC PLC inputs and outputs. Now, syncing and sourcing only deals with DC, period. Only deals with DC. So So every PLC we have down there has DC inputs. So we need to understand this syncing and sourcing. A method of connecting DC PLC inputs and outputs that utilize a negative comma. Sourcing is a method of connecting DC PLC inputs and outputs that utilize a positive comma. Digital on PLCs, signals that are represented by only two voltage levels, usually 0 and 24 volts. So every PLC that I've ever played around with that uses DC inputs are one of these. Analog signals, these are signals that are represented by a continuous variable voltage or current. I should put that with. Usually when we talk about analog, we're talking about voltages. And then we have another thing called current loop, a signal that uses current to represent digital or digital analog. That should be analog or digital signals. By the way, I just worked on this weekend, so watch out for mistakes. So I'll upload this. I've uploaded it to the website, by the way, but I'm gonna have to make some changes from it. So we have what we call a 4 to 20 milliamp. This is probably the most popular, where 4 milliamps represents 0% and 20 milliamps represents 100%. So if this was digital, what we would do is we would use 4 milliamps would represent a 0 and 20 milliamps would represent a 1. If we're using it to represent analog information, then a quantity of 0 would be represented by 40 milliamps, and then 100 and then 20 milliamps would represent the quantity of 100%, and you could have any current between that. That make sense? I'm listening.
I'll talk to you about it.
Why we like to use current? This was used in industry, and it's still out there. It's been replaced by an interface called differential interface. The problem we have with using a voltage is that electromagnetic interference gets voltage into conductors. But this electromagnetic interference can't generate a current, because there's just not enough energy or coupling there, right? You understand? So anytime we start dealing with what we call high resistance circuits, then we're very, very concerned with what we call EMI. You know what EMI is? Electromagnetic interference. And the problem we have is that when we put current through a conductor, it generates a magnetic field. Well, if that magnetic field, you don't see that little ammeter over there? All I'm doing is swinging a conductor through a magnetic field. That's all I'm doing. Well, anytime I put current through a conductor, it generates a magnetic field. And if I've got another conductor by that, it does what? It'll induce a voltage in there. Well, when we're dealing with things that are switching, then the magnetic fields are going to change, right? Y'all notice I don't get any. This thing is sitting here stationary, I don't get any water. What do I got to do? I got to move. Well, what AC current does is it generates movement of the magnetic field. So any AC signals we have, or any AC power we have, has a tendency to generate electromagnetic interference. Well, the problem is I'm using that feedback to control the speed of the motor, and I've got to run that feedback from my sensor out there through copper wire. Right? You understand? And if it goes through a noisy environment and I don't spend a lot of money on my cables, then it's going to screw up all of my sensor readings and stuff like that. Well, the problem is that this does not really generate a lot of current, but it generates a voltage. So that means if I can use a current as the signal, then it means these got 4 to 20 milliamp is basically noise meters. I mean, you'd almost have to have a nuclear explosion to get because that EMI, that electromagnetic interference, is a voltage. It's not a what? It's not a current. Y'all understand that?
Now, on this right here, currently, is it the same as digital? Like between 8% and 57%?
Don't know. That's a good question. I'm sure there's a, now these 4 to 20 milliamp current loops, but these, and we used to teach how they did this. And basically what's nice about the 4 to 20 milliamp current loop is that the way these devices work is as long as you don't exceed the range of what's capable on your inputs and your outputs, this is immune to the length of the wire. So that means you could run these things 1,000 foot or you can run them 100 foot. And what the driver does is puts out enough voltage to give you 4 milliamps for a 0 and 20 milliamps for a 1, which was rotor-rotated. So if you don't have broke wires or stuff like that, or if you don't exceed the voltage output of the amplifier, so the amplifier could only go up to 10 volts. But so if you got enough resistance in there where it took more than 10 volts, then you have problems. But anything below that, now we use what we call a differential interface, which is also immune to noise. And it doesn't require current flow all the time. The biggest disadvantage of current loop is you always have water in your conductor. You always have current flow. Current flow means power, it's not much. But, you know, if you've got 5,000 units out there running 4 to 20 milliamps, that's a lot. NPN, we're not going to get into trouble. A lot of this, if you get into solid state, you'll take this. The solid NPN are basically solid state devices, usually used to switch positive DC, and then PNP are solid state devices that you use to switch negative DC. And then we have what we call relay outputs. So these are outputs or inputs, but these relay output modules, these can be used to control either AC or DC. Now, the advantage of these guys is they're extremely fast. The advantage of this one is you can either use what? Diesel racing. But what you find out in most of your control circuits, extremely high speeds is not, on the outputs are not always necessary. Inputs have to be high, sometimes have to be high speed, but not outputs. Okay, y'all go ahead and take a break, guys. The examine on and examine off took a little longer than I thought it was going to take. I thought it was going to be a review. Nope. It's on PowerPoint. The PowerPoints are up there. There's just a few little mistakes in it. What I'm going to do is the processor, microprocessors, or the CPUs inside the computers cannot subtract. Well, how do they subtract? Well, they subtract using something that we refer to as 2's complement. And basically what I'm going to do is I'm going to write down I'm going to use 4 bits because we don't have much time. And I'm going to do so if I count in binary using 4 bits, this would be equal to a 0, but it's also equal to a positive 0. That would be a 1, 2, 3, 4, 5, 6, 7. Now unsigned, that would be an 8, 9, 10, 11, 12, 13, 14, 15. And that's all I can represent with 4 bits of binary. So instead of using 16 bits, I'm just going to demonstrate this using 4 bits. Okay. Now unsigned, this right here would be a 0. I'm sorry, this would be a 0, this would be a 1, this would be a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, the processor has no idea whether it's doing it. I mean, what you do is you use these flags depending on whether you're using unsigned math or signed math. Over here, this would represent a 0, which has no sign. This would be a positive 1. This would be a positive 2. This would be a positive 3. This would be a positive 4. This would be a positive 5. This would be a positive 6. This would be a positive 7. This would be a negative 8. This would be a negative 9. I mean, this would be a negative 8. Sorry. This would be a negative 7. This would be a negative 6. This would be a negative 5. This would be a negative 4. This would be a negative 3. This would be negative 2. And this would be a negative 1. Now, if you don't understand it or not, what you see is all my negative numbers has the most significant bit of 1. All my positive numbers have the most significant bit of 0. So this would be true for a 16-bit. This is what gets people confused right here. This is a technique called 2's complement. So if I was to come up here and add two numbers, okay, I'm going to add two positive numbers, and I add 3, and then I come up here and I add that to 3. Then this is going to be a 0 with a carry 1, a 0, a carry 1, and it's going to come up here. So that's, I'm sorry, carry of 1. So this is going to give me a what? 6. So I added two positive numbers and got a what? Positive answer. Let's say I come up here and I add 4 or 5 plus 4. 5 plus 5, that's good. Okay, so 5 plus 5. This is going to be 0 with a carry of 1. This is going to be a 1, right? This is going to be a 0 with a carry of 1. That's going to be a 1, which is a 10 unsigned. But all of a sudden now it comes over here. But a 10 is right where? Here. So a signed number, but what happened is my overflow flag just set. So that means if I'm dealing with signed numbers, I would check that overflow flag to see if it changed the sign. So if it changed the sign, that means if I add two positive numbers and it comes up negative, that means I actually have a positive answer. Does that make sense? So because it changes the sign bit. So the overflow bit sets, but it don't do the carry. That makes sense. Now let's say I add a number that causes a carry. And who determines what bits, who determines what flags to set? So if I was a programmer and I'm dealing with signed numbers, then by George, I'm concerned with that overflow flag. Because if that overflow flag comes up and is set, it indicates the answer has the wrong what? Sign. If my carry bit sets, it means I exceeded the range of the numbers. So if I'm dealing with unsigned numbers, I'm going to be concerned with the what? With the carry flag. So if I come over here, what would cause a carrier? Let's say I'm going to add 8. We'll just add 8 plus 8. So this is all I've got. That's all I've got. This is the size of my register right here. This would be a 0, 0, 0, 0 with a carry of 1. This sets the carry flag. So now all I know is my number is 1 power of 2 greater. And that's all you'll ever get, by the way. Dealing with 16-bit numbers, all you'll do is just have one carry. Right? You understand? So if I add two decimal numbers and I keep them at 4 digits, then all I'm ever going to get is just one carry digit, right? Does that understand? Of course, in binary, I'm either going to carry a 0 or I'm going to carry a 1. So if I was dealing with signed numbers, and what's the beauty about this? Let's say I subtract two numbers. Well, the processor can't subtract. So what I'm going to do is I'm going to represent a 5. And what negative number do y'all want to subtract from that? Huh? Okay, so let's subtract a 3. So what I'm going to do this right here, I'm going to do what? This is 2's complement. That's a 2's complement. I'm going to add those together. So if I come up here and if I take 5 and subtract it from 3, what should my answer be? 2. Okay. So what I'm going to do is I'm going to add these together. So this right here gives me a 0 with a carry of 1. That gives me a 1. This gives me a 0 with a carry of 1. This gives me a 0, and I lose this to the carry bit, but that don't make any difference. If I come over here and convert this to the decimal, what do I get? I get a 2. So what the microprocessor or what the processor does, the processor itself cannot subtract. So what it does, it subtracts by addition. So if you tell it to subtract, it takes the regular number, it takes the 2's complement of the subtrahend and adds it. So what I can do is I can subtract without having subtraction. But taking the 2's complement, it's the way I learned it is you take your positive, what you want right here. So let's say I want to see what a -7 looks like. And then what we do is we take the 1's complement, which means invert. So what would I do? I go 1, 0, 0, 0, and then you add 1 to it, and that's the way the 1's that's why it got the names 2 complement. So it means that would represent a -3. Well, when I look at a -3, oh, I'm sorry, -7. This represents a -7. There it is right there. Now, one of my students showed me this, and I don't know if they cheated on it or not, but this is so cool. What you can do is you can take your binary number and invert everything past the first 1. So I write down a 1, and invert means to do what? And there it is again. So this is a 7, and this is the way I'd represent a -7. So I thought that was so cool. So basically all the processor would have to do is either invert the number, so the processor can invert real easy, and then do what? Add a 1 to it. And that's the way it does math. So the processor does it with something called 2's complement. What we do though is we sacrifice one of our most significant bit as our what? As our sign bit. So if it's considered to be a negative number, if I'm doing sign math, then if it's got a 1 in it, it's considered to be a negative number. If it's got a 0, it's considered to be positive. Now what's nice about your PLC, if you don't display this in binary, Alan Bradley's going to display it in decimal. So if you want to put in a -52, then by George, all you do is put in a what? A -52. And then the PLC takes care of converting it to 2's complement.
-5.
Yeah, -5.
Just one time,
So here's 5. Here's a 5. First of all, I write down the positive equivalent, and then I invert everything past the first 1. So here's my first 1. So I would write this down, and then I would invert this. I'd invert this. I'd invert that, and there it is, -5. So no, you're trying to do, this is a negative, it's a 13 in unsigned numbers, right? You understand?
I don't understand when the 1 is the first 1 on the
There's -5 right there. That's -5. 1, 0, 1, 1. That's a -5. So what I did is I wrote down the positive equivalent of the number, and I inverted everything past the first 1 in my answer. So here's my first 1, so I didn't invert that. So there it is. There's a 1 and 1. What did I do with it? Okay. What did I do with it? Okay. Now this is the representation of a -5. Don't try to go 1, 2, 4, 8 in your head, because this is the representation of a -5.
Right. So
I go over here and look at my chart on the negative side, and there's a -5. See, and here I came up with the same thing. So you're trying to do 1, 4, 2, 8 for your negative numbers, and you can't do that.
All you have to do is write down the plus number, then bring down the least significant digit, and flip the rest of it.
Invert everything, yeah, that's exactly right. Bring down the least significant bit. Right? And then invert everything else.
I was trying to.
Yeah, most people that's been in binary try to do that 1, 2, 4, 8 code, that 1, 2, 4, 8, and add them up, but this is a negative number. This is not a positive number. And we represent it in something we call 2's complement. But what's nice about two's complement is that you can do the math, you ignore the carry, so you ignore the carry, and you come over here and you add this is a 5, right, you understand? And this right here is the representation of a negative what? A negative 3. So this is a positive 5, a representation for a negative 3, and what did I do? I just added them together. And I came up with a positive 2. Which is what 5 minus 3 is supposed to be, right? You understand? So how did we subtract using 9's complement, using 10's complement? We subtracted by addition. We subtracted. What did I do with these numbers? I added them. I subtracted by addition. We learned something called 9's complement. So if I came over here, let's say I want to subtract 8 plus minus 3. Okay. What I'm going to do with the 3 is I'm going to subtract that from 0, and I'm going to generate a bar. I'm going to make this a 10. So I'm going to come up here, and that makes this a what? A 7. Now I'm trying to do 8 plus 3, but I'm doing it by what? Subtraction. What's 8 minus 3? 5. Okay, so now what I'm going to do is I'm going to use the 9's complement instead of that 3, and I'm going to say 8 plus 7. What's 8 plus 7? 15. I ignore the carry, and I came up with what? 5. So 9 is a method that we can use to subtract by what? Addition. In decimal, we call it 9's complement. In binary, we call it what? 2's complement. So you can subtract from 0. You can take a binary number and subtract it from 0, and you come up and get the 2's complement. Or how he got the name was they take the 1's complement, which in computers that means invert everything, and then we add 1 to it. Or we can invert everything past the what? This need. And we come up with a representation of a negative number, but what it does, it allows us to subtract by what? Addition. So what I wanted to do is I wanted to take a 5 minus a 3. 5 minus 3 is what? 2. But I took 5 plus this number right here and still came up with a what? 2.
There goes the addition.
Yeah, so what 2's complement gives us the ability to do, it gives us the ability of representing positive and negative numbers. But what it really gives us the ability to do is subtract by what? Addition. So that means my microprocessor, I says I want to subtract this number, I want to subtract. Well, what it does, it treats everything like signed numbers. It changes the sign of the subtrahend and adds, right?
Was this gonna be on the test?
Whose complement? No, I just wanted to get you a feel of what these carries and these overflows were.
Okay.
So carries means it's because basically this is transparent to you because you're dealing with a computer, and a computer can make things appear like they're not. So we can take a 2's complement number and display it as a minus decimal number for you, right? That's what a computer can do for you. But what we're trying to do is explain when do we have an overflow? When do we have an overflow? If I add 2 numbers together and come up and get the wrong sign, right? Not a carry, an overflow. There's a difference between an overflow. An overflow indicates you exceed the range of the signed number. A carry means you exceed the range of the register. So that means if I've got a 16-bit register, the biggest number I can represent is 65,535. Well, what if I add something to it? What if I take 65,535 and add 1 to it?
Let me ask you this.
Well, I just exceeded the range and the carry did what we said.
What if you were subtracting from that?
Well, if I subtract and it generates a bar, then we set the carry flag.
I'm talking about your integers going 0 through 7 and -1 to -8.
Yeah, that's because we're only using bit 8
So
bits.
you could subtract 9, you just have to go into a 16-digit.
No, we could. It's just that we're either going to generate a borrow, we're going to generate a carry, or we're going to do something like that. So what we'd say is we'd come over here. What do you want to subtract?
I was just thinking.
Do we want to add? Huh?
9.
Okay, so I'm gonna add 9, that's a positive number, and 6, which would be 1, 0, 1, 0. I add them together. Okay, so I'm adding a positive number and a negative number. What should my answer be? This is a what? Positive 9. This is a what? Negative 6. So what should my sign be? Well, it should be positive. Okay, so I come up here. I will come over here. Can't do that. Okay, can't subtract that. So I'd borrow a 2, make it a 1. Borrow a 2, make this a 2. 2 minus 1 is 1. Okay, came up to be perfect. No, it didn't. Yeah, I subtract. I had to subtract wrong. Thank you. Yeah, I don't know what I was doing. I do know how to subtract in binary, by the way. So this would be 1. Okay, I did what here? I had to borrow. We borrow 2s. It's just like 10s. We borrow what? 2s. Okay, so I borrowed a 2 from here, made that a 2, borrowed from the 2, made this a 1, made this a what? 2. 2 minus 1 is 1. 1 minus 0 is
1. But you borrowed that 1, so it's technically a 0 there, correct?
no, we borrowed it. We borrow a 2. So in decimal, what do you borrow? This is what you learned in decimal. So let's say I have 83, and down here I'm going to subtract 55. Well, when I mark this out and make this a 7, that you borrow the base. Okay, I understand. You borrow the base. A lot of people have put a little 1 up there, right? But you borrow the base. I don't know. I got to think about it. I know I'm doing something wrong. Oh, we're adding. We're subtracting, right? So let's go ahead and do it. And we're going to do it by addition. So 6 would be. Yeah, this is my problem. I'm subtracting when we're supposed to be subtracting by addition. This would be what? 1. This would be a 1, 0. Yeah, and now this was a 9, this was a 6. We expected a positive answer, so the overflow flag would be a 0 because we added a positive and a negative number, and we came up with. We expected a positive answer. We got that, and this right here would be the carry. Now, if I use this, if this was unsigned, this would still be a 9, and this here would be a 10, which now gives me a 16. Well, I can't represent 16. So now I would be concerned with the what? The carry. So if I'm dealing with unsigned numbers, I'm gonna be concerned with the carry. So the carry tells me I either had to borrow from nothing or I exceeded the range of my numbers, right? You understand that? So the carry bit is kind of misleading because it's set during subtraction. If you need to borrow from your most significant digit or your most significant bit, that sets the carry flag. Or if you exceed the range of addition, that sets the carry flag. If I'm dealing with signed numbers, I'm going to be interested with what? The overflow flag. If it's a 1, it means what? It means I got the wrong sign. If it's a 0, it means I got the right sign. I received the range of my sign number. So if I hit 1, I've exceeded the range of my sign number. If I get a 0, it means I did. Now we're just dealing with 4 binary bits, and that's what I'm trying to do. I'm trying to tell you these flags. So the overflow flag is kind of like a carry, but it only deals with what? Sign numbers. The carry bit is also a carry body flag.
So what do you do with the carry?
Well, what you would do is if I was dealing with signed numbers and it came up to be set, then if the number was positive, I would know it's really supposed to be what? Negative. Or if the answer was negative, I know it's really supposed to be what? Positive. If I get a carry bit, then I would just use the carry bit as part of my number. Right? You understand? So I get all the way up to 65, or I get all the way up to 32. What's 2 to the 16? 16 bits. So 65,535, well, if it's set, right, you understand, I know I've actually got one more power of 10, which would be, 65,536, 128,562 or something. And I
Not
know
that much.
to the 16th, I'd probably have to use a calculator.
65,536.
That's to the 16th. But to the 32nd is what we was looking at. If we added one more bit, that would be 2 to the 7th.
4,209,000.
No, to the, oh, you got my card?
Yeah. He's eating yours.
My,
Hey, I'm proud to say I cheated.
so here we're dealing with subtraction, same thing, we have, okay, so what can subtraction? One of these could use immediate addressing, or one of them could be a constant, but the other one has to be a what? One of them's gotta be a register. They can both be registered. Or we can have one constant and one register. Right, but I can't have two constants. Because if I always wanted to subtract 3 from 5, I would just use what, 2? Y'all understand that? And then we've got to specify a data file for our what?
Yes.
Destination. You understand that? Yes or no? And this is the same thing true all the way down the line now if you understand addition. So, same thing. I could repeat this every time. 2 operands hold the source data, right? Source A, source B. Either or both can be what? Or one can be a register and one can be a number. I understand that. And then we got to specify what? A destination. So this is multiply. Exact same format as the what? The add. The same format as the subtract. The same format as the multiply, right? Same format as divide. If you went over division. Division. 2 registers hold the source data, register A, register B. Either data can be a register or both can be a register, but one could be a source and one could be a number and one could be a register. So one of them uses immediate addressing. One of them uses register addressing, not register, direct addressing. The other one, they could both be used to direct addressing. I got a processor in my mind. I got to watch out. Well, this is division. Same syntax, right? You understand that? Exactly the same. These are some other math instructions. Whether your PLC supports these or not, you need to look at the PLC. I don't know what's supported by the I hope it's set up to communicate with it. I think it is. So we're offline. So let's look and see what we have here. So here's timers, counters, right? Okay, what am I doing wrong? Oh, sorry, wrong thing, right here. That's the problem with Logic Pro. They're different places. So here's my math. So here on this PLC, we have what? You know, see that? So we add, subtract, multiply, divide, square, negative number, 2 digital. So this would take a binary number, go to digital. FRD, which is from digital. This would take a digital number and go to binary. GCD, I'd have to look that one up. Okay, Grego. Woo, thank you. Then over here we'll see what, then we should have another one that's got ASCII, micro high, trig functions. So this guy here does not have any trig functions. See, they're all grayed out. So this PLC, advanced math, This has ABS, SVP, SWP, DCD, and ENC. Is that in there? That should have been that first list. So these are available on this PLC. Now, all of these could be available. I don't know what the 504 has. We don't have one connected up. But this might be something you look at when you get on your PLC to see what math functions are available to you on that PLC. All we got is the MicroLogic. This is 1100 right here.
I'm just trying to figure out where in an automation process you need those
What?
trig.
Well, anytime we're trying to deal with arcs, you're thinking about digital ons and off and stuff like that, where I see things moving at angles. So I'm trying to control a arm right here, and I want to know what degrees it's at. Okay. Well, not even robot or an arcing type of controller. And I want to stop it at 30 degrees. I want to stop it at 40 degrees or something like that. Well, then we're going to probably have to deal with the tree function.
Use those, IPs, open,
Proportional bias?
yes, 20 would be 0, and 16 would be like 75%.
Yeah, so proportional, what we call proportional valves, which come into play in hydraulic circuits a lot. Those you open and you depend on how much flow you get through, depending on the degree position of the valve. So yeah, you know. So this would be like if I had where I have a analog sensor, position sensor out there instead of a digital sensor that gives me a voltage that represents a position. And then I would have to take that voltage, which would represent the vertical line on the right triangle, and I could solve for the angle, right? So I could set the sign. I knew the maximum output that I get. So see, y'all talked about that. So yeah, but it's not used all the time. So what we're saying is that what you get depends on what you buy. So that means if I wanted the trig functions for my application, because I'm the engineer and I see a use for the trig function, then I'd make sure I bought a PLC. That would be embarrassing, right? You go out and buy 1,000 of these little guys, and you say, well, dang, they don't have signs. What did you just do? You bought 1,000 of stuff that's not any good to you, right? Because you need to do that situation. Or either that or you got to use another piece of equipment that give the PLC that, and now that's going to add extra cost where you could have took care of it with buying the right PLC. This is the program that's actually this is the program that's running this up here. It's running those at different sequence. And I would like to see y'all write that with what y'all know now. How many rungs? Don't count the end rung. 6 rungs. No, the end don't count.
But 0 does.
Oh yeah, sorry. So yeah, 7 rungs. Thanks, Larry. I forgot this is a computer. In real life, in a motor controls, we would not call that rung 0. We'd call it one. Yeah, rung 1. Yeah. Even I get it. Remember, I'm dealing with computers, and computer 0 means something. Listen.
I'm just looking through after this. I know everything be you after.
Now what we do is, and this is what we talked about. So we have these bit registers, right? You understand? We got B3. Some PLCs have a B3 and a B10. If your Alma PLC has a B10 register, that means you got 512 what we refer to as internal coils. Motor controls, we call them control relays. So in motor controls, we have 3 categories of relays. We have control relays. And what that means is the contacts never leave the control circuit. All the contacts are within the control circuit. A contactor means you have you have two types of circuits. You have a control circuit and you have what we call a power circuit. And so your contactors, you have contacts that are in the what? Power circuit. They're not in the ladder one. So that would be like me, like this program back here. I have two relays outside. Well, those relays are not part of my PLC, right? But I have to generate an output to control those. And then we have what we call motor starters. Motor starters are contactors that have what we call overloads on them. And what an overload does, it detects if the motor does not start, if the motor stalls when it's running. So instead of burning up the motor, we have a detection out there that detects if the motor can't get started, or or we make it try to develop too much horsepower, then it kicks what we call the overloads. So if you got a contactor that's got overloads on it, then that's what we call the motor starter. And that's the only three that we got. Now, PLCs, we've only got two. We have what we call internal relays. That would be similar to the control relays and motor controls. And we have contactors. Contactors would be the coils that have what? Output ports. So those outputs are not part of your PLC diagram. So if I want to turn on a light, you don't see a symbol for a light. Right? You understand? If I wanted to turn on a light in a motor control circuit, we would use a symbol for a light along the L2 side. So on motor controls, you could have true loads, not coils. You could have true loads inside the logic, but they got to be low current loads. Your high power loads that require real high voltage, those are going to be outside in your power circuit, right? Y'all understand that? So that means that I've only got so many outputs to work with. I think the 1000, the MicroLogic 1000, I think it has 6 outputs. I can't remember how many inputs it works, but we can look at that. So I've got 6 outputs that I can control something outside my ladder diagram, right? Understand? So that means if I'm going to use a coil that don't need an output, then what are you supposed to use? You're supposed to use one of your bit coils. So those are internal relays. In PLCs, we call them, so bit B10 does not turn on the motor. B10 is just in there for control. Standard stop station, which I will need to start putting in the diagrams. I think after the third lab, they're going to be required. Which means if you're on a 504, you don't need to use those switches like switches. You need to use them like push buttons. Which means you got one that's normally closed all the time. And when you start it, you do what? You just click it. Click it through, bring it back off. And then, yeah, so all these are bit coils. That's a bit file. I don't need that. Of course, this is an internal coil right here. This is an output, right? By the way, you can put comments and symbols all day long. But if you upload your program from a PLC, there's no symbols. So when you download it to the PLC, you don't download the symbols. Right? You understand? So if you upload that program back into your computer, there's not going to be any symbols in there. But if you upload it and you have the diagram still up, and you don't download it, right, you're going to have the symbols that you put in your program. Y'all understand what it is?
So when you download the PLC,
symbols don't go.
you close out of it, you need to work on that program.
And you didn't save it or something happened or you lost it. So that's what happened to this. I don't know where it's at. But I knew it was in the PLC. But when I did the original drawing, I had all these labels and everything on there, all the symbols labeled, all the comments and stuff like that. Well, since I couldn't find it, what did I do? I uploaded it from the PLC. The PLC itself does not care about symbols. It does not care about comments. All it cares about addresses, right? Addresses, that's all it cares about. Addresses and instructions. So what I'm saying is that if I was to load this program in and then go online then I would have all my labels and everything that I put in the original program. But I couldn't find it the other day. Well, that's not true. I screwed that up. I do sometimes. But this is what we'll get into later on. These are called compare instructions. This really brings in the power of the PLC. This is something you cannot do with motor controls. You cannot do a greater than, you cannot do an equal, you cannot do less than or greater than with relay logic. You just cannot do it. But when you get a PLC, not only do you get all the stuff that you did in motor controls, you also get a computer, which means now the computer can do what? Math, it can do compares, it can do.
You did work for you.
Yeah, it can do a lot of it for you, which decreases the number of runs that you have. Yeah, so that little thing that's doing all that reversing and everything, it's the 7 runs. When this runs up here, I've seen it run, right? By the way, another thing on outputs, 24 volts on PLCs is becoming extremely common. And why 24 volts? No, it's considered non-major. Considered the real strong, called very low voltage. Your power circuits are still going to be high voltage. So most of your current PLCs have a 24 volt power supply on the PLC. But that is not intended to run output. That's just intended to run the input, because they require almost no current. So that means your outputs usually require an external power supply. So up here I'm using this power supply. Y'all can't see it. That runs my outputs. My inputs are being run off the internal power supply.
I got a question for you. How much voltage goes to the telephone line phone?
Depends on whether it's ringing. When it rings, it jumps up to about 80 volts.
Is that much?
So ring voltage is a lot higher than phone voltage. And that's the way your phone knows when it's ringing. So even though you got 2 wires coming in,
Two very small wires.
very small, well, there's no real current. You know, so one is constant, runs the phone, and the other 2 goes to a higher voltage when it rings.
I just remember when I was a teenager, I was wiring up an extra jack at mom and dad's house.
When it rang,
Somebody called while I was wiring.
shocked you.
It was a shocking experience.
Now my cousin did that, but he was stripping them with his teeth.
That's even better.
Or at least that's the way the story goes. But you'd have to know my cousin.
Terry was.
No one, Terry. I got to remember where I'm at. I probably didn't need to do this. It was probably already in there. Wasn't it? Oh, yeah, but it's going to change it to untitled. I need to back there. And then I did change that push button though. Oh, what I like about the Siemens PLCs, it changes the whole behind to the color, so you can actually see it. So notice the first one up there is always a home and open, and it shows the display because I'm using a diamond here closed. So this is actually a normal close button. This is eventually what we're going to try to go to, where not only do you have to write the programs, you also got to wire the PLC up to do that. Unfortunately, you can't get it quite yet. So we got some sensors. We got a metal detector on it. This guy here has an analog port on it. So we have a rheostat, we have a potentiometer on it, and then we have what we call an optical interrupter right here, which we'll talk a little bit about. The one back there is, I don't know how many lines of code that is. That's like maybe 4 lines. And this is what I was telling somebody. Originally, when IBM was buying programs from people, they paid programmers for what they called KLOCs, which was thousands of lines of code. So what that meant is that the more lines you put in your program, the more you got paid. So people would deliberately write very inefficient code. Then when they got in ties with Microsoft sold them an operating system, and they wanted to pay them by KLOCs, but Bill Gates would have nothing to do with it. He says, because you're penalizing me for writing efficient code. So you shouldn't pay them by KLOCs, you should pay them by basically speed. How fast does the program run? Because the more rungs you put in your program, the slower it does. Right? You understand? In the old days of PLCs, we would literally get enough rungs that it would mess in because it wasn't scanning inputs at that time. So what we had to do was duplicate the rung. If we had a very high priority rung, a very high priority input, we would duplicate the rung, and that way it would scan it multiple times in the scan. Now we have something. Now they finally use something called interrupts, and hopefully we'll get in time for that, where you can literally cause the program sequence to change, so you can set up high priority stuff. Another thing that we didn't get into is that counters and timers, especially counters, are getting so important. You can understand in manufacturing, keeping up with counts is very, very, very important. The problem is that if you have a counter that's and hardware, you know the difference between hardware and software. I noticed that's in the first book. What's hardware? That's physical hardware. And then we have software. Software is what? Programs. What's nice about programs is programs are changeable. In hardware, you got to tear things apart. But what you'll find out is hardware is always faster than software. So if you get into digital and you put a counter, an integrated circuit that's a counter, it would flat wipe out a what? Programmed counter. So what they're starting to do is they're starting to put counters back in these PLCs. I mean, we're talking about hard counters. They're actually inside the chip. And they refer to them as high-speed counters. So the 1100 has a high-speed counter in that, which means it don't take up any lines because the counter's there. All you do is specify what to load that counter is. So if you put a counter instruction in your program, it is literally running a program that simulates a counter. If it's got a high-speed counter, then by George, there is a true counter inside that thing. The 1100 counters can count. One of them is 40,000 kilohertz. That's 20,000 kilohertz would be 20,000 counts in 1 second. That counter has the ability to do it. But you're going to have to use a dedicated input, right? You understand? So you can't have a high-speed counter and never input. So if you got a high-speed counter and you have something that needs to be real fast, like keeping up with the speed of a motor. In the old days, we used to use analog generators. So the faster the motor ran, the more voltage the little generator would put out. We call them tachyons. It's becoming more and more perfect. And then we had to take that and bring that into the PLC. And then we had to convert it to what? Digitally. So more and more we're using what we call encoders, which is nothing but a wheel with a bunch of slots in it, and it's spinning and it's sending digital what? Pulses. And you get these motors, some of these DC motors and some of these AC motors, some of these DC motors, up in 7,000 revolutions per minute. And we can't count them every minute, so what we do is we put a lot of stripes on the thing, and we might count it over a second, but we might need 30 pulses over a second. So these encoders have got what? a lot of wheels on it. I mean, a lot of slots in it. And we're talking about trying to control the speed of a motor and it's running at, 1,800 revolutions per minute. And I'm trying to control that speed and I'm trying to bring that into a counter that runs off the software. So a lot of your PLCs, I don't know about the MicroLogic. The 1100 has, I think, 2 high-speed counters. I think it uses port 0 and 1 if you use it. I know the Siemens has high-speed counters on there. I think the Siemens actually has some high-speed, has internal timing on them too. It's actually built into the hardware of the computer. I'm not sure about this, if it's got any hardware based timing. So there's our math function, guys. Any questions? So don't look like we're going to get in lab. Y'all go ahead and take a break and we'll come back and finish up our inputs and outputs and then we'll be in lab all the next class. So when y'all come in, Wednesday, we'll go straight to water. Huh?
No math
Test
today.
is this week.
What's,
Monday.
wait a
Next
minute,
Monday.
what's on it?
Well, since we're not going to cover anything, I can go ahead and put it in. Normally, we don't put it up until the class before the test. But since we're not going to cover anything new, I'll go ahead and put the third view up there.
You sure did appreciate that. Sure.
And to,
You can't answer financial aid. I'm an instructor, I don't know financial aid. You need to get in contact with your detail and figure out what that's going to be. I have no idea. Just a good question. So that would be like asking me. Donald Trump's on that. That'll be something.
Before we leave, I want you to go back over the S thing again. S4, S5. I'm fine with it. It starts in the book.
status
The status sheet.
The status register. What we call a status register. Alabama calls it a data register. Or the S register. On that one. Well, the S register keeps open flags. That's where your flags are going to be at. That's where that counting register is at.
You say something about interrupt?
Yeah, we'll do with that.
As in interrupt of what? Non-maskable, maskable, all that stuff.
All the microprocessor stuff.
Okay, you said something about
Well, I think this is the last of the book. I think storage is in chapter 1.
operand. You said something about that earlier?
What?
Operand.
Yeah, operand those.
How about, you don't say anything about opcodes? I remember those too.
Opcodes are binary. So those are binary. So opcode is the binary number that represents an instruction. We don't deal with
And it
operand.
works on the operand, right?
Yeah.
See, I remember that.
So opcode is the part of the instruction that tells it what it wants to do.
Right.
Then the operands are what the instruction operates on when required. So like that end instruction down at the very bottom, that has no operand.
On the end?
Yeah, that's automatically put in there for you. So there's some numbers there's some that don't have operands. Normally operands only come into play. This is when we talk about math, logic. So math, logic, and sequencers and all that kind of stuff in PLC is what we do. So you remember opcodes?
Opcodes, non-maskable was the highest. You gotta deal with it.
Gotta do it.
What's called IRQ. That's interrupt what you
Yeah, it's a massive number.
MMI.
Non-maskable. So normally non-maskables are for extremely high values.
Well, I was just trying to figure out how the S status return make that fail rate.
Well, what you would do is you'd choose one of those bits that you can see it. If you choose one of your low bits, it's going to be so fast that you can't do it. Right? So that means if that thing was running at, if the clock was running at, let's just, so if the clock was running at 2,000 hertz, which is going to be a lot faster than that, or, you know, then if I use that 0 bits, that's going to be running at 1,000 hertz. If I use the 1 bit, it'd be running at 500 hertz. If I use the 2 bits, it would be running at 250 hertz. Because what you do is you get a power of 2 every time. So your first bit is what we call a divide by 2. Then it goes divide by 4, divide by 8, divide by 16, divide by 32. So you don't want to use this one because if your light was flashing at 1,000 hertz, it would be on all the time. These guys right here are flashing at 120 times a second. And to us, they look like they're what? On all the time. So what you would do is you'd use one of these upper bits, and you can actually see it. When you bring up that output register, you can actually see which one you want to use. So what you could do is you could look at that and count it how many times? 3 times. And every time your count goes valid, you'd turn your light on. And after 3 times, you would stop it. The book shows you how to use what they call a cross-coupled timers. Y'all see that in the book? Where you use this one. When this one gets complete, it triggers this one. When this one gets complete, it triggers that one. And what it does, it just sits there and flip-flops back and forth. It becomes what we call an astable multivibrator. But you got to use 2 timers. Well, the problem is we do that all the time. We make light flashes all the time. So what did Allen Bradley give you? They gave you a register that does what? Just sits there and counts. And all you got to do is pick out how fast do you want it to count in multiples of 2s, how fast you want it to count, and just use that to flash your lights. And if you want to do it 3 times, you would do what? You bring it into a counter. Every time you got a counter enabled, you turn on your light. Every time the counter was disabled, you turn it off. After 3 counts, you would reset it and you'd be ready for the next one.
Oh, well, I got mine working. Not that way.
Huh?
So I got mine working, but it's not that way.
Yeah, well, that's the problem. But if you don't know, you don't know, right? And the PLC makes things available to us on things that we do all the time. So like flashing lights, we flash lights all the time. You know, so why not give us a counter that does what? Just sits there and counts all the way up to 65,535. And I just come up here and do what? Just pick the bits. It's just like when I'm counting. You know, if I come over here and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, when I get to 10, that only counts 1, right? And then I'd start over again right here. So this guy right here would be changing 1 per count. This guy right here would only change 1 per 10 count. One more digit would only change 1 per what? 100 counts. Next one will only change 1 per 1,000 counts. But here we're in binary, so it goes in powers of 2. 2, 4, 8, 16, 32, 64, 128, and that would be how much it divides by. So you're not actually seeing the clock. All you're seeing is the least significant bit of the clock, which is a divide by 2. So if the clock's actually running at 2,000, the zero bit would only be running at 1,000. But you don't care about that because you're seeing 0, divide by 2, divide by 4, understand what I'm saying? So the higher you go up, the slower it runs. This is syncing and sourcing, guys. So these are inputs. These are outputs. Right? So syncing, we're dealing with DC. Syncing only comes into play with DC. AC basically has no polarity because it's changing so fast. So syncing devices uses a negative column. Sourcing devices use a positive column. So which one do you think is predominant? Syncing.
Thinking.
So normally we use negative, even your car, what car does your car use as a compass? You got a red lead and your black lead up coming off your battery, where does the red, black lead goes to? Goes to the chassis of your car, it's actually common. People call it ground.
Yeah, we had I remember Mercedes the other day, they got these, I call them low voltage cables, that they hook to the car before the battery's connected. Somehow cable got reversed. And it's pushing 90 amps through the car, supposed to burn the car up.
It should burn the battery up. They hook it up to the
Well, the
battery.
battery wouldn't hook up.
Oh,
They just plugged, they got someplace in the engine compartment where they plugged the positive and the negative somehow.
but probably the battery terminal is probably already out, or they might hook it up to the harness that goes to all the instruments.
So anyway, supposedly they burned the car up. 480 volt, 90 amp.
So a syncing input uses a negative as a common. A syncing output uses a negative as a common. Sourcing uses what as a common? Positive. That's the difference. So when we go down there, you got a 504, you got one syncing input, one sourcing output. For the sourcing output, you use positive. Now, to lights and light bulbs, that would mean nothing. Relays, it means nothing. Controlling the direction of a motor might mean something, right? Especially for doing the phone. Well, what really comes into play if I was to take one of these output ports and hook it up to an input port on another PLC. And we do that a lot. So if you go over there to the Amtro line, you see on the robot back here, it's got a built-in PLC, and it's using relays to run. It's using outputs, sending inputs into the Siemens PLC. So this is where the syncing and sourcing really comes into play. And sensors are either going to be syncing or they're going to be sourcing. So that determines how you want to do your outputs. Now, if I'm running a relay, does syncing and sourcing mean anything? No. If I'm running a light bulb, does syncing, sourcing, outputs mean anything? No. All right, you understand that? When it comes into play is why if I was going to take the output of a PLC and use it as an input to another PLC, which we do that a lot.
Now, aren't most electronic components either or? Syncing or sourcing?
Electronics,
Right.
mechanical don't mean any difference.
Right, I know.
By the way, this type is usually called a what? Even though they don't use NPN and transistors, usually a syncing output module is going to be called a device. It's going to be called a PNP device. I'm sorry. Syncing is going to be called what? NPN. And then sourcing is going to be called PNP. So if you ever see that on the sensor, it's going to, and I'll show y'all some data sheets from some of the sensors that you'll be playing around if you take the sensors class. And that's where they're designated. When you look at the data sheet, sometimes it's printed on it. But when you look at the data sheet, they're going to specify NPN or PN. So NPN is a sourcing device. NPN is a syncing device. So we would hook that up to a sourcing PLC. A PNP device is a sourcing, so we would hook it up to a syncing PLC or DC. For the batteries. So you think about power. So power to get current flow, we got to have a voltage and we got to have a common, right? You understand? So syncing provides the common. So that means something else is providing the what? Source. So that means if I've got a sourcing sensor, I would hook it up to a syncing input. So the PLC is providing the common. The sensor is providing the power. That makes sense. And if I hook it up to if I've got a syncing input, so it's a sensor, it's going to provide the common. So my PLC has got to provide the power. So my output's got to be a sourcing output, right? That makes sense. And, of course, this doesn't come into play in AC. I was looking at this little Series 1 PLC up here, and it uses AC inputs and AC outputs. The AC has no polarity, right? You understand that? Because it's one. Changes so fast. But when I start dealing with these DC modules, then we're either going to have sourcing, or we're going to have syncing, or we're going to have what we configure. Now, most of them now are configured. And I'll show you how to do it. So most of them, but you do it in groups. So digital syncing and sourcing, we're talking about digital. AC, this is digital. Analog, analog voltages, by the way, are usually from what? 0 to 10 volts. There are no advantages to syncing and sourcing inputs. The only difference is how solid states are connected. And that basically what makes a difference is, and this is where your exam and open, this is where your exam and open and exam close will change. Sensors, we have NP sensors, we have PNP sensors, and we have relay. What's nice about relay sensors is you can run relay DC and AC, right? By the way, I need to put, we have AC sensors. We have AC sensors, NPN, PNP, and relay. And AC. So I think the solid state limit switch that we have, that if you take the sensors class, I think we're teaching that. I'm teaching that next. Yeah, so this is the solid state limit switch. And that's AC. But if you look at the panel, it'll tell you the voltage that it's supposed to run off of. So that's an AC sensor right there. AC. So this is an example. Now, this is not a ladder logic. This is just showing you. What we have to do is we have to figure out, so the current flow through the input is always the same. So notice one of them uses, the one on the left uses this is a syncing. This is sourcing. But if we use conventional current flow, electron flow, notice if we hook it up right, the current flow through the PLC is always the same. So this is not line diagrams because we don't put load. All this is just showing you the circuit. That makes sense? So it's very, very important that you know that. So when I go out there and look at I can't remember what the inputs are. I think the inputs for the 504 are syncing inputs, so those can't be changed. And I think the outputs are sourcing inputs. Some use only syncing, some use only sourcing, some allow the end user to decide. And of course, more and more they're moving to what? Number 3. Yeah, you put a COM. So we have what we call a COM. So what I can do on my input module, if I make the positive COM, then it's going to be sourcing. If I use the negative COM, it's going to be syncing. Now, usually on inputs, they do it in groups. So that means you make a group of them syncing, you make a group of them syncing, you can make the other group sourcing. But inside that group, you can't change it, right? Does that make sense? They have to stay the same. And that deals with the number of terminals and screws and stuff you have. And of course, input modules can be damaged if connected incorrectly. Because we couldn't make the current try to flow through the module backwards, right? You understand, which is not good. Normally they're protected. So these are syncing inputs. This guy right here is a don't care on the top. What we do, by the way, we never ever bring information directly into the PLC from the outside world. What we do is we bring it through what we call an optical coupler. What an optical coupler does is it transfers data.
Is there anybody in here that needs to register to vote? It's not registered? Okay. Thank you.
Everybody here registered, I just don't think you register. You got any non-voters? So what we do is we couple, this is a solid unit, I don't know if we can get the PLC modules out, but usually if you take the module out, it's gonna be a little integrated circuit. It's either gonna have 4 pins on it, it's probably gonna be an odd color, it's gonna have 6 pins. And it's just it's an integrated circuit. But what it is it's got what we call a light emitting diode on one side, and it's got a photo transistor on the other, and it's all in there together. So what we're doing is we're coupling information through light, not through electricity. So that means if something happens, if we didn't put that optical coupler right there, you could have something happen on one of your input ports, and it could wipe out your whole PLC. Just blow it up. But what happens if you screw up real bad, it might blow up the optical coupler, but it don't hurt any of your other ports. So we do it in there to prevent what we call massive failures because we screw up something like that. Now hopefully you have another port that you're not using. So normally on a PLC, we usually don't use all the ports that we have available. If I screw up one of my input ports, what can I do? Move to another one, and you'll have to redo your program, right? You understand? But that's better. You could be back up and running before you come out there and have to do that. So these are called optical couplers or optical isolators. This on the top, this photo has the LEDs in each direction. So that means I can make this a positive common or I can make it a negative common. So that's really neat because most of your PLCs like that. So if you look at your inputs, you got a common. And it's not a sourcing, it's not a syncing. You decide how you hook it up. Well, what happens if I hook up one way, it would use one of the LEDs on one side. So if I hook up a positive common, this is right here would work. If I hook up a negative common, this right here would work. And the photo transistor don't care as all it's getting is pulse. So this right here is what we probably use now. This is the way the AC works. So what we do is we bring AC in. This guy right here converts it to DC. This guy right here limits the voltage, so we don't put too much voltage. This is called a Zener. It only breaks down to a certain voltage. And then it brings, so this guy sees DC. Well, this is what an AC module kind of looks like. But every one of them's got these optical isolators in there, right? So if I come up here, if this is rated 115 volts, and I put 2,000 volts on there, it's going to blow this little guy right here. But it don't hurt my PLC. It don't hurt the rest of my PLC. I lose one input instead of the whole PLC. This is an example of hooking up sensors. So this is an NPN sensor. So this is what? Syncing, right? So here we're using, both of them use a watt. So this guy right here, here's positive. But if I'm using an NPN sensor, I'm going to hook it up to a sourcing input. Because my sensor's providing the negative, so my PLC output's got to be, my PLC input has got to be providing the power. That makes sense? Okay. Now this sensor right here is a sourcing sensor, it's a PNP sensor. So what I would do on this one, I would configure a syncing input or a sourcing sensor. Y'all understand that? So source means this guy's going to provide the voltage. The other guy's got to provide the current. Right? Does that make sense? So a sourcing sensor hooks up to a syncing input. A syncing sensor hooks up to a sourcing sensor. Now that might be cool. Sounds like a good test question.
No, not really.
And what determines? Well, it depends on what's true or false. So whether I use examine on or examine off depends on what I want to be a true and what I want to be a false, right? So this is where those examine on and examine offs come from. Normally with push buttons, we use examine close. Y'all got it. Examine close, examine close. Examine close, examine open.
That's a long play.
So if I'm using a push button, normally we use examine close. If I use a sensor, it depends on what type of sensor. We okay? So this guy would provide a 0 if it's, this guy right here will provide a 0 if it's true. This guy over here will provide a 1 if it's true. Y'all understand? So this guy right here is a sinking sensor. It's going to provide a 0 if it's true. This guy right over here is going to provide a 1 if it's true. So on this one, I would probably set my input up as examine open, right? You understand? This guy would set my input up for examine close. So when these sensors is going to be where you use that examine open and examine close.
Now, are they designated normally open or normally closed, or do you decide that on how you wire them up?
I don't know what you're asking. So a sinking sensor, you have to do like this. So here's my input, here's my common
Right.
on my input. Okay. And then, this is the common, this is the input.
Right. My question is, are they set normally open or normally closed, or do you set that yourself?
Normally, you don't do that. What you do is normally a sensor gives you one set of contacts. Some of them give you a maximum of 2. I think we got one back there. The temperature probe actually has 2. It gives you one normally open and normally closed. Most of the time, a sensor gives you one contact. And it's usually normally open. So this doesn't even have a contact. A lot of times a PNT won't even have a contact. It literally outputs directly from the collector transistor. So when we come up here and let's see if I still got it. This is one of our sensors right here. This is our pressure sensor. And you can buy different ones, right? Y'all see the different ones. So this guy right here, if I ordered an OPSLA-IP, this is a what? This is a PNP. This guy would be a NPN. This would be a PNP, and this would be an NPN. Now they don't tell you it's sourcing. They don't tell you it's sinking. It's up to you to know that. What's that?
I was just saying, turn that with PNP or N.
Yeah. Right. And how many contacts this has, I don't know. It looks like it's got 2 out there. It might have 2 contacts on it. This is our NPN is sinking and a PNP is source. That's basically what you got to know. Now, when you get into, if you take solid state, you'll actually learn the difference between an NPN transistor and a PNP transistor. This guy right here, where does it say that at? I know it's in here, guys. Oh, we're looking for a PNP or NPN.
So 2 PNP normally open
Yeah.
switching DC output.
Okay, so this guy's got 2. This guy does have 2, but it's 2 what? Yeah, normally open. So this is a PNP. So this is pretty standard. So a PNP would go to would be sourcing, and we would make sure we hook this up or port up to what? Configure for syncing. So this is the output of, these are the ports on the 1000 PLC. Okay. And notice this guy here has 6 inputs. But this group's got a group of what? Commons. But it don't say plus or minus, it says common. So what can you do?
Whatever
You can make
want to
it
do.
source or sink. Right? So here's the power supply there that you hook up to your input. So your inputs power off the internal power supply of the PLC. Here's the DC common here for these 2. And of course, this does not say sinking. It does not say sourcing, because you make it what you want. Now notice down here, this has relay output. So what we do is we have a common for every port. And that's, right, you understand that? Those are the outputs. This is a relay output.
Well, let's see how it across the top, sinking into it. See that across the top? Oh, configuration.
What do you mean?
Up there across the top, it says wiring diagram.
Yeah, for syncing input.
So notice they use a negative common over here. And this shows a positive on this side, so this would be a lot. They don't really show the polarity. So here's the common right here, comes up, goes to this side. And here, so here's positive, right? Understand? So these guys have to be what? So it depends on, this is showing a solid state sensor. A lot of your solid state sensors, they're made out of electronics. And unfortunately, electronics have to be powered up for the work. So a lot of your solid state sensors are like relay. One of them's going to be your common, one of them's going to be your power, and the other one's going to be your signal.
So this is the wrong one. This is not the 1100. I didn't know what model we have. So notice on this guy, you got one shot at it. So this one you don't have groups, whatever one this is. I forgot the model. I'm sorry, you did. You got this guy here, and then you got this guy right here. So this is not the 1000. It's not the one that we got. The 1000 that we got, and that's what I wanted to do, and I couldn't visualize it in my head. I knew it didn't have this many outputs. But what you do is on these PLCs, it's kind of similar to the other PLCs, is that on the side of the PLC, you're going to have a label. And normally when they specify the microprocessor or the PLC number, then this is what you're looking at. So what you're doing is not this, what you're doing is you're looking at this guy right here. Kind of like we were on the Siemens over there. This is the actual model number. So they make a lot of model numbers off the 1100, but this guy right here, this number right here determines what version of the 1000 or 1100 this is.
So that number,
Huh?
number that we have to input that we're working with.
Right. But normally they understand that, and normally they'll put the model number out there. But then they might have several versions of that model. And that's when you got to go out and you got to look at the thing and actually find those extra numbers on there to get exactly what you have on your PLC.
Yeah, I was trying to find it.
On what?
I was not successful on that MicroLogics.
It's on the side. That's right. So it's on the side. If you look at the side of the PLC, it's going to be on the side like this.
So on the side of the PLC itself, inside the case, you know, those are in case.
Well, but they got a big space in between them. You can see down there. So we have a 1761-L16BWA. That's our MicroLogics. So I didn't write that down. This came out of the 1100 PLC manual, and what they do is they split their. They call, by the way, Allen Bradley calls plus. They call it the DC bus. So we have plus DCD, so that would be the plus DC bus. And then minus DCD would be the minus DC bus. So this is what I would want to do if I wanted to hook them up syncing. I would do what? I would use a what? Negative common. If I wanted to hook these up sourcing, I would use a positive. I understand that.
PNP policy?
Well, we're talking about the inputs. We're not talking about the sensors. We're talking about the input. So if I wanted to make some of my inputs, if I wanted to make them sinking inputs, then I would do what? I'd use a negative column. And if I wanted to make these inputs sourcing, I would use a positive column. But unfortunately, we can't do every one of them. We can't specify every one of them. So on a lot of these fixed PLCs, now when you have a DC, a rack PLC, normally you buy either a syncing module or you buy a sourcing module. And they are non-comparable. Because they power up down the rack. So since they power up down the rack, you can't jump what power supply you want to come into those modules, right? So these modular PLCs, you specify what type of module you want. So if you go and look at the 504s, I think the input module is a syncing module, and the output module is a sourcing module. And it's written on the PLC, right? I mean, on the module itself. I can't get the numbers off of them, by the way, because they got them. They got the inputs all wire tied together. And they don't have enough slack, so you can pull the module out.
So it's actually what module numbers those are, I don't know. That's because somebody told you.
They're on the door. If you open
Oh, they are? Okay.
They're at the bottom of the door.
PLC outputs, we can have either one.
Syncing, which means they use input and output, sourcing, they could be called PNP modules. PNP modules, they can be AC, or they can be relay. Now, what advantage does the relay have? And you decide if they're syncing, you decide if they're syncing, right? What's the disadvantage of relay?
They change it up.
They come out.
I'm sorry.
Relays are electromechanical devices, which means what? They got two things they can fail. They got two things that can fail. Not much. If you see the little relays, we got some over there. They're what we call reed switches. They're very, very small. They're not big at all. I'll try to remember to bring some of the little reed switch relays that we have over there. They're not rated at a real high current, but we don't use these guys to drive big loads, right? You understand? We might use them to turn on a light, but if I needed to control a 600 horsepower motor, I would do what we do back there. We'd let the PLC pick up a relay, and then we might let that relay pick up another relay, right? We can go through games going through relay. Another disadvantage, and it usually won't come into play very often, is the speed. Electromechanical devices are usually slower than solid state devices. I mean, if I needed extremely high speed outputs, then we're going to use the solid state device. If I'm not concerned with extremely high speed outputs, which I've never seen a use for them, I mean, I'm sure they're out there. But most applications, we don't really need extremely high speed outputs. So most of the times, relay outputs will work. What's nice about relay outputs is you wire them the way you want. And every output usually has its own column. So I mean, you could have one output sourcing, you could have an output 0 sourcing, you could have output 1 syncing, you could have output 3 running AC, right? You understand? So that's what's really nice about relay logic, is you're not tied to syncing and sourcing on the ports.
But you hear them click.
You're not tied to it, but will it not create problems if you wire it up incorrectly?
Well, usually anything creates problems if you wire them up incorrectly.
I guess what I'm saying, there's more room for error with those than if you just make one sync.
Well, the only problem you would have is that it don't care. I mean, it don't care. So if I hook up something to port 0 that's supposed to be on port 1, that's the standard mistake. If I hook up AC to port here, or we might run into problems if I put DC on one side and AC on the other. That's the only problem I see. If you put AC on both sides, right? But then you go to the wrong output. Then you go to a DC device. That could cause a problem.
So if you put DC, AC on the DC device, that can cost money.
Is there some type of protection where if you do wire it up?
Well, that would be you, that would be your protection. Yeah, I mean, you can put all kinds of stuff that would sense AC or sense DC, but normally we don't do that because that adds. We depend on our technicians. And basically, when you get into PLCs and stuff like that, most of the problems are what? Wiring. Operator error. So there's basic, this don't mean they're exactly the same, but they're, normally this guy here would have a diode parallel with it. But sourcing, we use a what? PNP. Syncing, we use a NPN. This is a device called a track, by the way, which is a solid state. We find these in solid state relays. Where you turn these suckers on and they're on, you turn them off, they're off, which is relay, and this is relay. Which then we can put what on relays? Syncing, sourcing, okay. So when you got a modular PLC, you usually don't specify either a syncing output or a sourcing output. Value one. So everybody okay on syncing? Everybody okay on sourcing?
Yes, I am so.
Your son? Any questions? Anything we went over today y'all want to go back over? I'm listening.
The only question I have, you want to go ahead and put the test review up?
I'll do it when I can. Legally, I don't have to pick it up until after next class.
Oh, I know that.
I'll try to get it up.
I heard you say something a while ago.
Yeah, I'm gonna try to pick it up.
I'll be looking for it.
I'll send out a, anybody sign up for that remind,
I did.
For the what?
that texting application?
I've been there to have remind, but I don't.
I signed it.
Yeah, I gave y'all the procedures on there, how to put it on your smartphone or whatever, and, which is pretty neat. You signed up. I'll look at that today too and see how many of y'all said you want me to do it for you. I think if you said, is it okay if I use your phone number, one of your questions on your search?
Oh, yeah, okay. So you can hook us up?
Okay,
Yeah, I can sign you up.
I'm one.
Hook us up.
Actually, I think I'm already signed up.
It would be hard, but you need to look at that instructions, because if you got the remind application, then you enroll in a class, and then automatically you can text from that class and receive from that class. If you don't sign up, if you don't put remind, then I can text you, and you can text me back, but there's a number, 80, I can't remember what it is. It's on that instruction that if you don't have the remind application installed on your phone, if you want to text me, you have to use that number. You know, you see it all the time. If you want to text so-and-so to this, and they give you a number, well, what you do is you put that number in there, and then in your subject or in your thing, you put the name of the class in there somewhere.
Let's see. I got a text from 334-239-0455.
What did it say?
You joined IoT 196, advanced PLC.
Yeah, it automatically sends you a text back when you just to see if you set it up right.
I did not download the app, but I need to download the app or.
If you want to, if you don't want to use that number,
I
and
found the number. I could care less.
but if you reply to that, you should be okay. But if you wanted to send me a number from scratch, that the procedure is on our on our Blackboard site under text messaging, and it shows you it's a 1. I can't remember what the number is, 8 something. I know it starts with an 8.
I am replying now.
And let's say, thinking about changing phone. This phone is just
I just
about
got- I just got-
outlived its.
Remind Larry Engelberg, I'm replying.
You got it. Hey, I'm
Will it
good.
automatically switch over? You got to say that. Same area.
You got it.
With what on
You said
there?
something about an app. You got to put an app on it.
No, no. I don't know what you, I've never known of something automatic. Sometimes they can, if it's the same model and the same operating system, sometimes when you go to the store and you buy it, they'll swap that stuff over for you sometimes. But if you're going from an Apple to an Android or something like that, the answer is no. If you go from an Apple to an Apple or ISO operating system, if you buy your phone at one of these retailers, then they may be able to swap all your apps for you. If not, yeah, it should have a list of the instructions is on there. No. I've been responsible for this class, this semester. That's all we're doing, guys. Anybody want to come up and get some help with something, then I'll be here. If not, I'm gonna load up and go over to the robotics lab.
I'm going home taking a nap.
Review will be here. I mean, online.
I hope. I'll send y'all a text. I'll send y'all an email. Usually when I post a review, I'll send y'all an email.
I get those.
You gotta say that twice.
It's what's nice about text messages is that it comes through instantly. Emails come up in your phone chat. You have your faucet state on your phone. I do too. But I've only got mine checking every 30 minutes and only when I'm connected to Wi-Fi. So I don't use data for email.
I got this big clunking chunk of data that I had when I was at USD. Purely for entertainment purposes, and I never did change it. It's kind of cheap. Entertainment purposes? Yeah.
I think I got
Saturdays?
16. Yeah, what is that, the beauty pageant for my granddaughter? A guy there watching Alabama game.
Purely for entertainment purposes. When you're out there in the summer, everybody, well, the game, can you work? I got you, babe. 16 hours, bring that hotel bill out, and we had just went to the AT&T.
Rollover?
No, the plant went from Nextel to Verizon, and they had these boxes, what are they called? Repeaters, and they wouldn't work right. Then they went to AT&T. Well, that hit me just beautifully, right? And we had this little device.
So you have an access point. Network we call that.
We had superb access. No, everything was in HD, it seemed like. I mean,
They have them all over the planet.
well, all we need, well,
Inside the building.
the control room, ours was just right next door. And, well, here's the tech shop. You go out the door into another door, and there it is. I mean, it was, what's that word? The bigger you do it, you get better. The resolution was off the chain.
Family.
Yeah. Oh man, it's beautiful.
So they can get those open networks, so they can.
Well, it was AT&T.
Open
That's
network.
what the boss's phones were. Repeaters, because sometimes we're going 3 stories down, and you got to be able to talk to somebody while you're working on this equipment. My phone worked just like that.
Oh, so you was they wasn't a repeater, that wasn't an access.
Yeah, it was actually
It
a
was your
repeater.
phone, it was that.
And we bought
So
this.
you went, I was thought you were talking about Wi-Fi, wireless. She's talking about actual phone.
That too. Somehow I got left open. I don't know.
Somebody did the password. They left it open, somebody said it is open.
Well, I had this friend with the office grad.
You knew where
He
it
was
was.
one of the engineers over there.
Yeah, so somebody set up an access point and didn't probably use the default password.
It was for the whole Texas. He had a way, well, he had a way where he would use our PLC log roll. It was first initial, last five letters of last
Oh,
name.
he set up a,
Whenever you came in the range, anywhere.
hotspot, they set up,
Yeah, you go up to his office. Oh,
and you can do that with your cell phone. We had
yes.
when we was up in Tennessee, I couldn't get my computer connected to their wireless, but my phone was.
Right.
So I set up a hotspot on my phone, and I would connect to their wireless through my phone. So that's what you were doing, you was connected,
Allegedly.
allegedly.
Is it on 189 or is it on?
I don't know what that is. It's a three.
Both of them. On the paperwork.
Okay, so let's move
Activity.
183.
183?
Yeah, we changed that. One was Logic Pro Lab, y'all went there.
So it's on 180?
Yeah,
189.
189.
Yeah, so this is the Logic Pro Lab, it's the same thing. So when I was looking at the activities, I got in the wrong section.
Okay.
So it's the same activity. And actually,
189. All right.
that's all correct.
Okay.
Okay, y'all were having one.
Yeah.
My sister has a baby.
Oh, she did, what did she know what it's supposed to be?
Oh, boy.
Everything's about okay?
Yeah,
Okay.
because his heart rate up to 80,
Oh, really?
so they had to.
Y'all have a good evening.
All right. So you gotta come back and see.
Or you got a scar?
Right across the street, there is
Yeah.
hydraulic pipe.
Or you got,
Just picking on.
Oh, ask him, is he gonna have it next spring?
Hydraulics?
Yeah.
Okay, we'll do.
I know what I'm gonna do.
my brother's wife, she all her children. Goes on the pelvis. Do whatever she wants to do. Not bad, I mean, I got that.
Oh, yeah.
I know. Some of the stuff that's
I say, when you gonna have that, you don't have it on Tuesday at 1 o'clock? And they usually do it right before the due date. Well, besides that C-section, you get to choose the date and time, most of the time, unless you have a problem. So what do you look at?
What you think is gonna be available for,
I don't know. Look.
going to the close on this?
So what am I looking for? I'm looking for meeting, I'm looking for NAT schedule. I'm looking for 16, 17, I'm looking for spray. Oh, this is what we got. This is what we put in the schedule.
Troubleshooting.
Shooting right here. 9 o'clock. Thursday.
What about electronic circuit?
Electronic circuits is a elective. So we only offer that class. That class has not made, we haven't had anybody ask for that class since we put it in.
Okay. Hydraulics, industrial hydraulics.
It's Thursday.
Same day.
Probably, my day. That's Tuesday, Thursday, let's get that up one, let's get that up Thursday, on top of it. We're going to go.
So what's AC/DC machine.
That's motors, that's you, they use the electronic. And it's the boy. That's gonna be on the campus. Right now, by the way, this right here might move. We got plans for this. What we're planning on doing is moving all the motor trainers over to Birmingham campus. And then, and we're looking at trying to buy some more motors. Move them over.
What's this?
So right now it's over here.
Okay, well,
The
I,
AC/DC machines might be moved to the other campus.
was it named something else before now?
Huh?
Was it named something else before now?
No, AC/DC. No, it was called, on the old bridge, it was called AC Motors and Trains.
That's right. So I've already done that.
You know, if you did unload blue trainers.
Yeah, the little blue train, yeah. So I've already done that, so that's not, I mean, I can pick that up. The only one I have left is the hydraulics and troubleshooting. And they all the same day.
The problem we have is people don't understand that we got two instructors teaching this, and we got to teach, basically 5 classes. So, if that's going to happen, I wish it didn't, but there's really no way in the world we could do it. Unless one instructor taught all afternoon classes, we could go to 5 o'clock. So these classes right here are 5 hours. So if they started theirs at 1, I mean, theirs would be out at 6. And that's why. So they all started at 9 o'clock or 5:30, so that means they're going to be, so we can get y'all out of here at a reasonable time. That's why they run that on. Boy teaches some classes that go late like that.
So which one would possibly pick up in the fall then? Because I know everything.
I don't have, and that's a perfectly legal question.
But
What we're doing right now on Friday, we're doing that mechatronic certification. And we've got to get that thing taught in 2 semesters. So what we're trying to do now is we're taking our normal annual schedule and we're moving stuff around. So and that's going to start in the fall. Supposed to start this semester here. We could do this class as part of that certification. We're going to teach this according to the certification. And most of them are already there. Other certification, intro to PLCs, that's part of the certification. Mechanics, some show. That's what industrial mechanics. On the certification.
I took,
So we're gonna, our program is going to, as far as what we offer in spring, what we offer in fall, it's going to change. Unfortunately, so right now, if you ask me what's going to be offered in the fall,
well, I understand that.
I
It's
wish I
just,
could tell you, what's going to be offered in the summer.
oh yeah, I forgot about that. But
Summer, I can show you what we offered last year, but that don't mean that's what we want this year.
Yeah.
I mean, normally that's what we've done. We offer basically the same classes every term. We offer from the previous year. So we're pretty much well on an annual schedule. But the problem is that problem that we're talking about now. We got to guarantee if they come into that certification that those classes are over in 2 semesters. So every class has got to roll, every one of them's got to roll around days and nights in 2 semesters. So troubleshooting is going to be taught every semester except summer. Troubleshooting will be taught 1 days, and next time it'll be taught nights.
In order to get, because I know during the summer hydraulics, it was either whichever one would be on during the summer would help But if that's the case.
Well, let's look. Now, this is not true. I can't, I wish I could say this is true. Well, let's look and see what we offered during the summer last term, which would be, back here would be in 15-16. And this was our spring. Now, that's the annual schedule we're working on, but that's going to fall apart now. Here's summer. And here we go. I don't know why she's got two. Oh, copy. She saved a copy. So this is what we offered last one. Now, commercial wiring, you've already had that though, right? You took
Yeah,
commercial wiring.
I'm down to these two. As a matter of fact, my concept of solid state is not showing.
I forgot to go.
So those are the only two troubleshooting in hydraulics. I know hydraulics.
Well, hydraulics is one of your electives, right? Yeah. Mechanics is also elective for you. Motor controls is not. It's second one from the bottom. It's not on there. It's supposed to be. Oh no, I'm sorry. It's in the AUT. I think NEC's not on there. Of course, NEC never mind. Yeah, it is. It's on there. You got sub. You taking it?
Which one?
Right here. You can get a substitute for that.
I did. We substituted. Well, that was back before they changed it. I substituted. What was it? The store called it.
Well, if it's not showing up, are you counting that? Who put in the course sub for you?
Nancy.
Well, it's not showing up yet. When did you run this off?
This is the newest one. I need to
Well,
check.
say they're not giving you credit for this. If you substituted this, they're not giving you credit.
Okay. And that might be the reason I ain't getting credit for my solid state.
No, it's you took it's not gonna show up here. It's not even showing up out of your degree plan, is it? Which solid state what solid state did you take? Now what's in your degree plan?
My degree plan.
What's course numbers in your degree plan? ETC, what course numbers in your degree plan? For solid state.
Solid state is ETC.
ETC what?
120.
Okay. Okay, come on guys. Where you at? Oh, it's down here. What's your student number?
1186391.
So ETC 108 is showing up out of your degree plan? That don't make sense.
Well, I went from residential, then I went to industrial. So when I took care of
Because
that,
ETC is not even showing up on your, is out of your degree plan. So we got ILT 166, you know what that is?
166.
Yeah, so you took an ILT 166 and made an A in it. Let's go here, let's go, let me go F10. Yeah, sorry, 12, IN, where's transcript at? Yeah, oops, yeah. No, it's transcript inquiry, see if that works. So you took ILT ET 154, which is residential wiring, DC. Okay. And
ILP 166.
motors and transformers. Okay. And you ain't got credit for that. That would give you credit for AC/DC machines. So right now it's showing up out of your degree plan.
So they will take care of it.
You took ETC 119, that's AC. Do you get credit for that? You got credit for AC? ETC 10.
Oh, this 2 years, so it was not on the blueprint. What that tells me what it is.
Yeah, that's why I brought your transcript up. So you've got, out of your degree plan, you've got ETC 108, which is motor controls. And I don't know why motor controls, something's going on, because motor controls has been on there since.
Yeah, I know, but when I changed over to,
No, we've had motor controls.
but you changed the title.
No, we didn't.
Yeah.
It's been it's been ETC 108 as long as I can remember. I know it was something before then. Yeah, so this is, I think you're okay. So down here it shows ETC 108, not in degree plan. Up here it shows ETC 108, making a B in it. Down here it shows you made an A. I don't remember what you made. See what I'm talking about?
Yeah.
So you probably need to go down there and talk to them about that.
Yeah.
You look right here.
Yeah.
There it is. Now let's see, so in your transcript, you took this spring, 1416. So there it is right there. Oh, and this, oh yeah, and you made a B. But over here it says you took it and made an A. So we need to figure out which one it is. See that right there?
Yeah.
And,
That's 1416.
and when did you take solid state? ETC 127 is digital.
Oh,
You didn't take
Oh.
you didn't take a solid state.
I see what happened, but it didn't fill. That's what happened.
We canceled it last year.
Yeah, it didn't fill.
We didn't have enough, we had one, that's the one where when we came back off of, it must be Christmas break for spring, we had one person signed up for the back. It might have been you, I don't know.
Yeah. Because when I came to class, it was another guy, and he said he had just signed up for it. So
And that's a shame because we're doing it this semester. No, we're not.
you're doing it. Well, we don't know what's happening for the summer. So
Solid state, we can't do it in the summer. Solid state is a 5 credit hour course. So if we taught it during the summer in an 8-week term, we'd have to make it 7 hours a day.
well,
We don't do any 5 credit hour. Oh, you want to leave your transcript?
yeah,
Oh, to see what these classes are?
yeah. You can get out of here.
I'm here till 2 o'clock. I was just gonna go over it. I'm fine.
104 is,
104 is blueprint reading. I know that one.
26.
226 is cable splicing. 154 is residential wiring. It's either lab or theory. I don't know which one it is. It's probably lab. EET 154 is probably lab. EET 108 must be theory. That's back when it was split. Now it's one class, by the way.
And 166 was
166 is the one showing up. That's motors and transformers. On that degree plan, it should be AC/DC machines. Now, if you don't have credit for that up in your program, we need to do a course sub for you. Because now it's not ILT 166. I don't know what it is. Did you get credit for motors and Did you get credit? Okay. Oh, well, let's see what's out of your degree. Oh, this is not going to show what this is your actual transcript. So this shows you what semester you took, what classes. So you hadn't had solid state yet.
that's when they dropped it.
Right. And we are doing solid state this term. We're doing it 9.
What about for spring?
So where's the schedule at? Here's spring. I know we don't do it in the summer. This is spring. Doing it days. Monday, Wednesday, 9:30 to 12:30. It's one of my classes, so
So that'd be Monday, Wednesday. So I would have to either wait till the fall again
for what?
for either hydraulics or
Hydraulics, pneumatics, or
no, solid state. I can do this spring.
Let me look at this. Let's look at this. So what you got is you got electives and you got required, right? So right now you have 22 right now. You need 22. You need one more class.
So I don't really need hydraulic.
No, I'm sorry. Those are split up. Where's the split up? I hate those. So where's our electives at? Here's the elective. You need 8 credit. You need 18 credit hours right here. You've already got 21. Why are you looking for stuff in there?
Oh.
These are electives, which means you choose what you got. You got one more class to take up here in your group. Okay. You've already got 21. It only requires what? 18. So you're trying to get classes down here. These are electives.
Okay. So I'm good on that end. So all I need to do is
You can graduate. Solid state. Oh, dang it. I wish you had took it this semester.
Well, I didn't know. I mean, I hadn't looked at it that way because
Well, for some reason in your mind, you had that you had taken.
yeah, because
That's your problem right there. Because we're doing it nights, so we won't do it. We'll probably do it. Oh, we are doing it spring, right?
yeah, you said they're doing spring days.
So you're doing that.
Yeah, 12.
That'll finish you up. So you might as well go ahead and do your graduation recommendation, baby. Go by the registrar's office and tell them you want an application for graduation. Go ahead and sign up tomorrow, you're on March and graduation. I gotta be there, you might as well. Get to put on your cap and gown and get down there and about 2,000 or 3,000 people out there. It's really, really top class. They got it down to a fine art. It's really nice.
Well,
And they
my
do it
next-
up, they do it up at the East Exhibition Hall at the Civic Center.
Mhm.
We couldn't do it here. We don't have enough space. I don't know, the gym over there is real nice. I don't think it's a big gym. I don't know how many they had when President Obama came. It was packed. Did you go?
No, I wanted to, but
You had something. I had something. You know, a lot of people's got, don't like him, but how many times did you
you get to see
say
your president.
the President of the United States came to your college?
And this is the
A
first,
community
the
college in
first
the state
community
of
college.
Alabama.
yeah, first community college that any president had came.
Yeah.
I mean, that's.
So that's a real honor. I got a picture of my ticket. He's a, that man can put on a speech. You might not like him, but if you come in and watch him, just his speech, he's just extremely comfortable with what he does.
I'm thinking about going in the air conditioning and refrigeration after this.
How you pay? Normally, a financial aid will only pay unless you change water.
So let's change one.
As far as I know, you don't take that from me because they started that because they don't want career students. We had a girl here before they set that law. Perkins will only let you change water. Now what you're on, I don't know. But we had a girl here that she was here, I don't know how many years. She graduated to what? She changed majors. She did all of ours. She moved, last time I saw her, she was in computer science. She moved into computer science. Smart girl. She just didn't like people. She was real shy, but she was extremely smart. And she was just so scared to go to work. That's all she did. So she was a professional student. So now Perkins is limited to 12 semesters. Whether you take one class a semester or whether you take a full load semester. After 12 semesters, Pale.
Yeah.
Are you on Pale?
Mm-hmm.
Well, that's what you need to do. You need to find out.
How much they got now?
See if not how much you got left. If they'll let you move over because you've already changed major. And you can understand why.
Oh, yeah.
What they're trying to do on Perkins is Pale is trying to do away with the professional student. So 12 semesters maximum, which if you came full time, had no developmental courses, then you could get 4 years. So if you transferred a 2-year degree into a 4-year program, you could get a bachelor's. And that's full time. And that's not one class. If you take out one class a semester, or you take that minimum 12-hour load, then that means odds are you're not going to be able to pull off the bachelor's degree. By the way, your bachelor's degree, if you want to move, University of West Alabama, they give you a block credit. They give you 2 years of credit into a bachelor's degree out of the technical program, out of our program. And Athens, but that's all the way up to Huntsville. They'll give you 2 years for a bachelor's. In fact, Athens is a strange university. They don't do 100 or 200 level courses. They're all 300-400 courses. Their intent is to give bachelor's degree option to community colleges. So Athens will get 2 years credit. Central Alabama will get University of West Alabama. It used to be Central Alabama. They'll give you 2 years credit. A technical program. Alabama A&M, you probably could get some credit from them too. Was that one? This is one.
Oh, that's Alabama State.
Alabama State.
A&M.
Yeah. So you can check with those guys to see what kind of credit you can get if you want to go. With both those, you have to basically move. UAB You can get credit for your academics, but they have no technical degrees. They have no technical degrees in life, so all theirs are
Well,
not applied science, they're all ASs.
well, thank you, sir. At least I know I.
So look, are you looking at taking all those classes?
Well,
So go ahead. In fact, when you leave here, just drop by and get your, am I your advisor? Okay. Just go back and get an application for graduation. And we'll fill that out and get you out of here next semester. And you might want to drop by financial aid since it's not crowded. And see what the options of you doing another degree change if you want to. Air conditioned refrigeration is a good program to go into.
well, I'm just trying to make it to my 60. If I'm military, again.
Oh,
Which
you're
is
right.
next year.
I could have retired. I'm in my 32nd year. I could retire. I'm 7 years over my retirement, where I could get my maximum income. Of course, the longer you stay, the more you get. But my wife, I told her the other day, I was thinking about retiring at the end of the spring. She said, I think that would be a mistake. So I'm not the kind of person that could